to introduce about the power behind rising stars of light. First of all, I'd like to acknowledge the strong support from Professor Alice Zhang from Peking University, founder of iCANX, and Professor Yuhong Bai, head of Light Publishing Group and Deputy Chief Editor of Journal Light Science Applications for initiating this, as well as the support from the whole ELSA, eLight, and LAMP team. We have 21 members. This photo only reveals part of them, but you can see girl power dominates, which I'm very proud to share. So before we get to Rising Stars of Light, I'm going to spend some time in introducing ELSA, which founded Rising Stars of Light. ELSA is a leading optics journal co-published by SciOmp and Nature Publishing Group. It targets at the most breaking results from all areas of optics, which makes it very unique as a top-tier comprehensive optics journal. So up to now, we have 11 years history, but throughout the past 9 years, our impact factor has been ranking among the top 3 optics journals, with the latest impact factor of 19.4. But one may have not noticed that even as a journal which is still growing, ELSA is already publishing more than 300 papers per year, which makes it the largest volume annual journal among the top 5 impact factor optics journal. And today we receive more than 2,000 submissions per year, and the publications have also received more than 2 million of downloads per year, so which makes us a giant impact in the community. So you can see we have received groundbreaking works from leading scientists, including many Nobel laureates. Leading scientists in optics talk to us to reveal more facts and facts about science. And UNESCO's International Year of Light and International Day of Light selected us as a golden partner. So with ELSA's impact and the optics community reaching to us, we grow to realize how emerging topics may bring transformative changes to optics and its cross-disciplinary topics, and how such fields have been less represented. So that's the reason why eLight is founded. To guarantee these ambitious targets, we formed a highly prestigious and diverse editorial board in which 40% of them are Academy members from all around the world. And launched for merely 2 years, eLight has rapidly become a highly visible resource in optics. Its papers in the past 2 years have received an average download per paper of 11,000 times, and average citations per paper of more than 44 times, average optometrics per paper of 50 times. So we actually are going to announce a big news in November, but I cannot disclose any details by then. So eLight is also widely accepted by our community. Its works have been positively and frequently cited by Nature, Science, and many of the leading journals. Meanwhile, reported by hundreds of highly visible science news portals. Now, we have received spontaneous submissions from more than 20 countries, and mostly from leading groups from in the world. And the dominant submissions come from US, Europe, and China. If you publish in eLight right now, you are going to enjoy a lot of benefits, including waive the publication fee until the end of 2024, and efficient workflow with the first peer review decision of around 1 month, headline highlights by both eLight and ELSA, and also news and views feature, commentary feature by ELSA, and of course, promotion of each paper through at least 5 social networks and 10 major science news portals around the world. All of our papers are going to be promoted through email promotion, and also on-site promotion by our editorial office and editorial board. So from another perspective, to help disseminate the important works in engineering-based researches, we launched the Light Advanced Manufacturing LAM aims to publish the top quality researches in all modern areas of light-based manufacturing, including fundamental and applied research, as well as industrial innovations. So because we are targeting at the top 10 top quality research in engineering based, so our target impact factor is 10 plus. So LAM has an international editorial board team with 42 members from 13 countries. Different from LSAT and eLight, 30% of the board members are from the industry, including the heads of the optics department of Google, Microsoft, and Apple, etc. And LAM also provides abundant author benefits, including first, it does not charge any fees at the current stage, neither from authors or nor from readers. Second, once the article is accepted, it will be pre-posted online within 3 days. And third, various kinds of channels are going to be provided to promote the papers. And last but not least, we provide the AI intelligence portraits of the corresponding author and first authors on the web page for readers to quickly understand the author's background and previous works. LAM is also famous for its feature issues. Its issue on holography has not only gained worldwide attention, but also is leading to a book in Springer. And right now, there are 4 special issues opening for submissions. We look forward to your contribution. Based on the platform of our 3 journals, we set up a series of light-branded events, which generated tremendous impact in the community. And Rising Stars of Light is part of them. And since 2018, we initiated Rising Stars of Light to spot the most brilliant young scientists in the optics world. And throughout the past 5 years, Rising Stars of Light have attracted close to 1 million online audiences and has been listed by International Day of Light as a worldwide featured event. And this year, we are very pleased to announce our Rising Stars of Light in 2 tracks with Professor Aidan Oskin from UCLA and Professor Martin Booth from Oxford, serving as the chairs of each track. So during application stage, we received qualified nominations from 4 continents and 12 countries. And after careful selection by our committee members, 6 finalists for faculty track and 7 finalists for before faculty track, they stand out and they are going to compete tonight and next Friday's night. And the awards for both tracks will be announced right after next Friday's campaign. Today is the final campaign for our before faculty track finalists. Now let's meet our committee members. And they are Professor Martin Booth from University of Oxford, Professor Nicholas Feng from University of Hong Kong, Professor Mona Jarrahi from UCLA, Professor Shang Zhang from University of Hong Kong, Professor Qihua Xiong from Tsinghua University, Professor Igor Aronovich from University of Technology, Sydney. Now, I'm going to hand over this session to today's moderator, Professor Yating Wang from KAUST. Yating, please.
Hi, everyone. It's very nice to meet everyone virtually. This is Yating Wang from KAUST. Let's first, it's very nice to meet everyone here. So let's welcome our first speaker, Zhou, postdoc from Stanford University. Zhou, the virtual stage is yours. Please go ahead.
Yeah, great. So let me start by sharing my screen. So can you see my screen?
Yes.
Okay, great. So yeah, so I will go ahead and start. So hi everyone, thank you for the kind introduction. I'm very excited and honored to be here today. So today I'd like to talk about my research on compound flat optics, and in particular, I'd like to focus on their applications. So I'm very motivated to dive deep into these topics today because over the past few decades, there have been tremendous growth and innovation in consumer electronics. And because the majority of the information we process is presented as visual, So their optical modules are becoming increasingly critical. In fact, the technology to enable those optics has been so well established that we tend to overlook their cost and complexity. But as we are further innovating those devices, we started to notice that their conventional optics do have limitations. They are fairly bulky, and they have fabrication constraints, particularly in the context of semiconductor manufacturing. And they also have limited design flexibility. That's why we need to stack multiple layers of optics. And this additional alignment and packaging can substantially increase the cost of the whole system. So the motivation of my research is to innovate those optics in order to bring down the size and the cost of the whole system. So the holy grail is to enable this ultra-compact optoelectronics where the optics and the electronics can be seamlessly integrated as a monolithic package. So in this scenario, the optics should be ultra-compact. It should also be CMOS compatible so that we can fabricate and package the whole thing using the same foundry compatible process. And in addition, it's highly desirable that those optics could also help offloading the back-end digital process so that we can have a tiny device supporting large-scale data processing locally. So how do we enable such optics? Recently, there's a new type of flat optics called matter surfaces have emerged as an ideal solution. So what is matter surface? We know that in conventional optics, such as lenses or prisms, they are fairly bulky because they rely on a three-dimensional profile to shape the wavefront. But now, in the context of matter surfaces, we can compress their thickness from centimeter all the way to submicron, as you can see from this schematic picture. A matter surface is essentially a planar nanostructure devices made of those artificial matter atoms. So if we can carefully engineer each matter atom laterally, such device can transform an input wavefront into any desired optical functions. And such capability turn out to be very useful because they can potentially mimic the functions of many free space optical elements ranging from lenses, grating to freeform surfaces, but with a very thin form factor. And because of such potential applications, there has been tremendously impactful research on matter surfaces over the past few decades. So there have been many pioneer work on developing the material platforms in the visible and near infrared, followed by multifunctional, tunable, and all the way to mass production of wafer scale devices. However, despite all those great advances, there are still a number of fundamental and technological issues in this field. The first one is the design space, because we're compressing the whole engineering space from 3D to 2D, and that inevitably leads to the reduction in design space. So how do we overcome that? The second limitation has to do with applications, because matter surface has gone so long, but today we are still relying on the conventional optics because they are great for imaging. So is there any critical functions that only matter surface can provide? So in today's talk, I'd like to discuss my efforts to address each individual challenge. So I'd like to start with the first part. So by the time I started working on matter surface, I noticed that most of those devices are fabricated as a single layer using standard top-down lithography and etching, but they have inherent limitations associated with their design freedom. The reason for that is because the matter atoms are already densely packed in a subwavelength manner. So it's very challenging for us to incorporate additional design freedom without affecting the performance of the other functions. So ultimately, it's necessary to search for new design freedom on the third dimension to transition from single layer to this closely stacked multi-layer dielectric matter surfaces. So the critical challenge of this platform is the fabrication. And it's worth noting that the 3D processing of low index polymer has been well established. We can use techniques such as 2-photon lithography, but in the context of high index dielectrics, which is necessary for many matter surface study, this fabrication is very demanding. So we took the first experimental initiatives to enable this platform, and that allows us to really enable new regimes of wavefront engineering. So based on our platforms, we first tested its capability in the context of metal lens. So we fabricate this multi-layer matter surface, which can focus multiple wavelengths at the same focal distance. So this is the optical response. You can see that we are focusing multiple wavelengths with very high NA and with more than 60% efficiency at both wavelengths. And because of its large numerical aperture, we can also use our lens for imaging. For example, here we are imaging those elements on the scale of wavelengths, and those tiny elements can be clearly resolved under both wavelengths. And we can further expand the capability into holography. So for example, here we design and fabricate a multi-layer matter surface which can project two different hologram images under two different wavelengths. And this is our measurement result. You can see those holograms have a pretty fair large field of view and high efficiency. And we can also expand its capability into complex three-dimensional light field control. So in particular, I designed this 3D holograms clogged with continuous transformation. And this means that as I'm scanning their far field, we can see the two hands of a clock continuously rotating along the z-axis. So all those demonstrations does show the extended capability of this new design freedom. But this is just the beginning. Our bilayer platforms can be considered as general, which can be applied for many interesting studies, including multi-channel imaging, polarization, and orbital angular momentum. So now you can see we have this very sophisticated platforms, but what is the application? So is there anything unique that our capability can provide? So I'd like to move on to the second part, which is to use our flat optics for imaging processing. So we know that nowadays the imaging processing has become a very important technique in different science and engineering disciplines. And among all the techniques, the edge detection is one of the most fundamental processes. So basically, this process has been used to detect local intensity and phase gradient. And as a result, they can filter out the unnecessary information while being able to preserve essential geometrical outlines. So the conventional way we perform this edge detection is by means of convolution. So suppose we have this image, then we have a kernel that rasters through the image, and at output, we can review the edges. But the limitation of this process, as we can see from the video, is the scalability, which means that the number of kernel operations will highly dependent on the size of images. This also means that if the image contains a large number of pixels, this computation could potentially be very demanding. But ideally, the goals for big data should be fast, real-time, and low power. So in order to overcome these limitations, we aim at switching the computing platforms from electronics to photonics, because photonics have many intrinsic advantages in terms of speed, polarization, and power consumption. And in particular, we designed this very special type of non-local matter surface, which can directly engineer the spatial frequency of an image without Fourier transform. And we engineer their long locality in order to perform a particular type of mathematical operations we call two-dimensional Laplacian, and that's equivalent to two-dimensional edge detection. So we are the first group to experimentally demonstrate this 2D edge detection, and that allows us to really push for its applications. So because our device is ultra thin and flat, that means that we can easily integrate our device with other imaging system without adding additional space. So we first tested such capability with optical microscope. So here we put our differentiator on top of the optical objective. And for imaging, we took some biological transparent cell as a test charge. So we can see on the left columns, those cell boundaries and shapes are not very clear because our camera essentially can only detect intensity, not phase contrast. But as we inserted our differentiator, now those edges and boundaries become very clear. So that means that with our tiny edge detector, we can convert a bright field microscope into the dark field. And as a second demonstration, we want to demonstrate an edge detection sensor for the application of computer vision. So for this case, we fabricate a large-scale devices which are directly integrated with a camera sensor. So the two parts can be considered as a monolithic smart camera. So for imaging, we took some real-life objects we can see on a daily basis. So this is a flower mold I purchased from the supermarket. So it's something we can get very easily. And as we image this flower mold using our camera, this is what we see. You can see that now those boundaries of the flowers now gets clearly reviewed. And then we can also see the defects on the mold, which is not very visibly clear. And that means that our camera can also potentially be used in the food and the defect inspection industry. And all of this is a static thing, but we can also use our camera to do real-time imaging processing. For example, we took this bottle, and as we are moving this bottle around in free space, and this camera can automatically capture the edge information of the bottles, and all the computation is computed at speed of light with no time delay. And now we have demonstrated many interesting applications in this context of image differentiation, but there are potentially many more opportunities we can explore. For example, we develop a very unique material transfer techniques which allows this differentiator to be encapsulated in a flexible substrate. This case is PDMS. So this means that now the device can be tunable. So as we stretch the device, we can really get a wide range of mathematical operations. You can see this is our original image. And this video shows the process image as we stretch the device. You can see now we can get a wide range of mathematical operations by changing or stretching our device. And also we can use our flexible device as a very convenient interface which allows conformal mapping and heterogeneous integration. For example, we can easily map our device on a curved imaging surfaces to enhance the performance of a conventional imaging system. We can also do heterogeneous integration with exotic materials and nanophotonics to enable this hybrid compound meta optics. So we envision that our results could enable many new applications in the field of defect inspection, sensing, and biological imaging. So that's all for my today's talk. And I'd like to acknowledge all the researchers and professors during my career, and thank you so much for your attention.
Thank you so much for the nice talk. Are there any questions from the committee members? Oh, yes, Mona.
I think Nicholas raised his hand first, so
okay, yeah.
Yeah.
Okay, thank you, Mona. I really appreciate it. Yeah, so I'm really excited about all of the latest advancements, but I just wanted to get a sense of how is the technology or idea different from the early stage of Fresnel zone plate and the kinoform lenses. They appeared earlier, and some of the actually breakthroughs also stem from Stanford and I'll say different university studies. So could you please comment on that?
Well, yeah, definitely. I think the matter surface has to do with many advantages. The first one is the resolution. We can control the wavefront because in the context of Fresnel lens or any surface relief gratings, if we want to engineer the wavefront in the context of like 2 pi phase change, we have to structure the surface with 3D based relying on the height to control the wavefront. But if we want to pattern this 3D profiles within the sub-wavelength resolution, that's very challenging. So that highlights the advantage of matter surface because we only need to change the implant dimension to shape the wavefront over 2 pi phase coverage. So we can really engineer each phase front at the sub-wavelength resolution. And that allows us to realize like high-end metal lens and hologram with large field of view. And another advantage, I think, with matter surface is a multifunctional capability. Because we are using high-index nanostructures, which can support multiple functions or encode multiple functions at different wavelengths, polarization, and incident angle, so we can flexibly integrate a lot of functions on a single chip. And I do think that this multifunctional capability is one unique advantage of matter surface. And I think a third advantage of matter surface is that the devices you mentioned are basically for spatial wavefront control, but for matter surface, we can also extend its capability to like time control or engineer the spatial frequency of light. And that means that we can do like edge detection or imaging processing. And I think that's something that conventional optics cannot do.
All right, thank you. Any further questions? Probably Mona.
Yeah, Thank you very much for the great presentation. So I was wondering, now you have gone to 2 layers of these nanostructures in your metal surface. So can you comment on the level of complexity if you want to add more layers from fabrication point of view, and at the same time, the additional functionality it might add if you're able to fabricate those in terms of new kinds of transformation optics?
Yeah, thank you for the questions. So it's definitely much challenging if we want to extend to more layers. So in fact, I do think that our fabrication is a novel and a very unique part of this project, because we already managed to pass around this tedious and demanding conventional multi-layer lithography process. Because imagine if we were to employ like conventional multi-layer lithography, we need to do dielectric growing, patterning, and encapsulation, planarization, which is very challenging for highest vibration nanostructure, and the secondary dielectric patterning alignment. So this is very demanding. So instead, we pass around this process through material transfer. So we pattern the metal surface through different substrate. And one of the metal surface layer is patterned on the germanium sacrificial layer. That means that we can transfer that layer of pattern by dissolving the sacrificial layer. And then we align and bond the 2 layers using a high precision 2D material transfer stage. So we could get this alignment done with the resolution of 1 or 2 microns. And recently we even managed to push that within 1 micron limit. And because with this process, we can ensure that each layer can be fabricated with high fidelity, and then we align. So this is much easier to scale up to 3 layers. In fact, we have a result which showing that by stacking 3 layers, we can focus like 3 wavelengths, 4 wavelengths with high efficiency and diffraction limited focusing. So in terms of more functions, I think currently we stop at 2 or 3 layers because we think it is a time we incorporate other methods to expand this function. For example, we expand the design rationale by using algorithm-driven approach such as inverse design. So with that approach, we substantially expand our engineering space beyond the conventional design approach that I show in this presentation. So with that, we can already implement like 4 to 5 functions all on the same chip. But in the future, definitely, depending on the applications, and if we do reach the physical limit in engineering space, we'll consider to stack more layers on top of it.
Thank you.
Yeah.
We may only have one quick question from Martin.
So earlier in your talk, you've said that you wanted to do things with these very impressive metasurfaces which could not be done with conventional systems. Is there actually anything in your talk here which couldn't be done with a conventional system? Because many of the things like optical differentiation and so on could be built through an optical system using lenses, for example. So is there something here which really couldn't be done using a conventional system?
Yeah, that's a very important question because it's also a long-standing debate. But you are certainly right. The image differentiation could be done using conventional optics, but that generally requires like a 4F system. So we have to separate or create like the 2 lenses at like a focal length distance. So that really creates a lot of like additional space in the imaging system. So it's not very flexible to put that into other systems. So with our approach, we can do this edge detection without a Fourier transform, which means that as we put the device directly in front of the device, in front of the image, then we can directly see the edges of the device. So that means that we are compressing the whole space from 4F to almost 0. So that means that this device can be easily integrated with conventional systems to conveniently add functions. I think that's the very distinctive advantage of metasurface.
Mm-hmm. Okay, thank you.
All right, thanks again, Zhou, for the very nice presentation. Due to our tight schedule, we'll have to conclude the Q&A here. Thank you again. And our next speaker is Luciano Masullo, postdoc from Max Planck Institute of Biochemistry, Germany. The virtual stage is yours. Please go ahead.
Thank you so much. It's a pleasure to be here. I will share my screen. Do you see my presentation? Do you see my presentation correctly? Yes, right?
Yes.
Yes.
Okay, excellent. Thanks so much for the invitation. It's a great pleasure to be here in this final for this award. I'm Luciano from the Max Planck Institute of Biochemistry from the group of Ralph Jungmann. And today I want to talk to you about the journey that I've done in my career, like going from the diffraction limit of light to the angstrom scale in optical microscopy, microscopes that use light. So first of all, let me introduce you briefly to fluorescence microscopy. Fluorescence microscopy is a key tool in life sciences because it allows us to get images such as the one you're looking at, that this is a cell, and it lets us to have very high sensitivity and to label with specificity different proteins and different parts of the cell. And it's also of low invasiveness compared to other microscopy techniques. So it's also compatible with live cells and with minimal invasive approaches into studying life systems. But it has a big problem, which is the resolution. So this is the nuclear envelope of a nucleus of a cell. And the nuclear envelope has pores, and these are the pores of the cell. But as you can see, no detail can be appreciated because of the resolution of the microscope. And the resolution of the microscope is limited by the diffraction limit of light, which is around 250 nanometer for the best optics that you can get. We're talking about far field optics, of course. And basically it states that if there's, due to the wave nature of light, if you have 2-point sources that are imaged with an optical system, for example, a microscope, if they're closer than this 250 nanometer distance, they will not be able to be resolved and the image will look blurry like this. So this is a fundamental problem of fluorescence microscopy. It has many advantages, but has this resolution issue. So super resolution fluorescence microscopy has been developed in the last 15 years, more or less. And it let us go from an image such like this to an image such like this. So basically now we can actually see the pore and the structure, and we can even image in 2 colors and see different proteins in these pores. Super resolution was basically pioneered by Stefan Hell, William Merner, and Eric Betzig that won the Nobel Prize in Chemistry in 2014. I think this is a nice example of the power for interdisciplinary because they are physicists who won the Nobel Prize in Chemistry for applications in biology. So, and the super resolution microscopy methods can be divided into 2 families: the targeted ones that are basically based on laser scanning microscopy with engineered light and different transitions that are used into the fluorescent molecules, and the stochastic methods that basically make the molecules blink and they are localized in space sequentially and stochastically. They are all based in the transition and the engineering of the fluorescent states of the molecules. So during my PhD thesis, I initially started by using and developing modalities in the super resolution field. I worked on parallelized live cell nanoscopy versions of the STED microscope. I also used STED microscope applied to neurons, in which you could reveal supramolecular details that were not possible to see otherwise. And I also worked on 3D storm, that is the stochastic technique, so that you can get also resolution in the axial stuff, so 3-dimensional. And you can go from diffraction limited to 2D super resolution to actually 3D. Here the color is encoded in 3D. But all this super resolution approach, this first generation of methods, can one problem. That is, okay, the resolution is way better than the diffraction limit of light, but it's still limited. So it's around 20-30 nanometer resolution. And molecules are still in the scale of 1 nanometer. Each individual protein, each individual molecule is in the 1 nanometer range. So can we go farther than that? How far can we go into the resolution? So the second part of my PhD thesis was how can we get in the sub-10 nanometer resolution fluorescence microscopy. There was one work pioneered by the laboratory of Stefan Hell called MinFlux, in which they coupled the structural excitation and sequential excitation of light with a donut-shaped beam with a single molecule localization. And in this work, pioneered by Francisco Balzarotti and Stefan Hell, they demonstrated that the localization precision of molecules using these kind of schemes can be improved basically by a factor of 10. So using much less photons, we can get similar precisions to the camera-based approach, or using the same number of photons, much higher precisions. And like sub-10 nanometer resolution was demonstrated for the first time. In my PhD thesis, I expanded the theoretical framework of this method to include also other methods that were around and were developed before and also after, including single molecule confocal tracking, orbital tracking, MinSTED. And also we could predict that new methods could be done, and I will talk about that in the next slide. We also did some work on how these methods could be extended into 2-photon regime. And with this theoretical framework, we started to say, okay, what are the best experimental implementations that we can do? How can we improve this sub-10 nanometer nanoscopy? And for that, you also need to take care a lot about experimental stuff. So we developed a software package to simulate aberrations and to simulate donut-shaped beams to get the actual optimal configurations for this kind of excitation of the single molecules. And we also developed methods to create experimentally these donut-shaped beams efficiently. Also, last but not least, it's super important to actually have instrumentation that can perform these complex experiments with a microscope. So we developed open source software in Python to control all these experiments. And then I focused on 2 projects. One was to get to the limiting speed that MinFlux can achieve and actually couple it to lifetime information. So the fluorescence lifetime of the molecules. So we term this microscope pulse interleaved MinFlux or P-MinFlux because it basically is based on having 4 beams that are actually static in space. They're not scanned, but actually they are interleaved in the nanoscale time. And with this type of excitation into the different molecules, you can achieve super resolution film or lifetime imaging at sub 10 nanometer resolution, and also tracking dynamical imaging of the single molecules with 1 nanometer precision and really high temporal resolution. Actually, the temporal resolution in principle is only limited by the repetition rate of the laser or the fluorescent rate of the molecule. And then also another project I developed was RustMin, which is basically a version of MinFlux that can be implemented in any confocal scanning microscope because it basically scans a donut beam over a single molecule. So basically, you just have to modify a confocal microscope by adding a vortex phase plate to generate a donut beam excitation. And then you switch, instead of having such an image of your molecule that is like a Gaussian image, you get like a dark spot where the molecule is, and this improves the localization precision by roughly a factor of 10, and you can also get sub-10 nanometer imaging. This video is how the acquisition looks when you are imaging many frames in the confocal microscope, and every time the molecule pops up, you see a dark spot where the molecule is, and then you can reconstruct the image. This is DNA origami. But then, so this was 2021. Then I went to do my postdoc here in Germany in the group of Professor Jungmann, and we said, okay, what's the actual limit? Are we really limited to the sub-10 nanometer scale, or we can go even farther with an optical microscope? Can we get into the intramolecular regime? Can we get really into the atomic scale with optics, with an optical microscope? And the answer is yes. And this is what I have been working in my last 2 years, my first 2 years of postdoc, and it's called resolution enhancement by sequential imaging, or RESI. And basically, it's revising the principles of single molecule localizations. You basically have these single molecules that blink or switch between a dark fluorescent state, non-fluorescent state, and fluorescent state, and they can be localized with a certain precision that depends on the number of photons, right? And so, for example, if you do DNA paint, that is the technique pioneered by the Ralph Jungmann's group, that it's based on the transient binding of 2 strands of DNA. One has a fluorophore and the other one is actually binding the target. But this is actually general for any single molecule localization technique. So if you image a structure such as this, and there are 2 targets that are closer than the precision of the localization of each of the molecules, then you get a cloud of dots like this, and you can distinguish it from the other cloud of dots that is farther apart, but you cannot assign the localizations of each of these to the actual target, and you cannot resolve these 2 targets that are closer to the localization limit. Even if you get many localizations here, you still cannot resolve it. But what about if we actually take the same type of target, let's say a protein, and we encoded it with different sequences? We assign one DNA sequence, or it could be actually one color, to this target, and to the other one, we assign another color. And they are identical, indistinguishable, but they are now labeled with different sequences. Well, that creates the following situation. You have 2 clouds that are spatially actually overlapping, but that are separated in the DNA sequence space, in another space. And then once they overlap, even if the limit of the precision is broader, you can find the center of this and then reach a much higher precision. This precision actually switches from this law of the single molecule localization precision that has to do with the number inverse square root of the number of photons to actually square root of the number of photons times the square root of the number of localizations that we get per target. And with this, we can get actually down to the Armstrong scale. And so how do we apply it in cells? We do stochastic labeling of a protein of interest. We label it with many different sequences stochastically, and this is the image of a nucleus of a cell. These are the nuclear pores that I showed you at the beginning, and this is a 3D image. Here color encodes 3D, and this is 3D DNA paint, so classical single molecule localization. And with Resi, we can go into this kind of resolution. We can go really into the Armstrong scale in precision. And if we do a model-free averaging of the structure of this nuclear pore that we are trying to image, we actually see that we resolve for the first time in the history of super resolution this dimer of proteins that is in the 10 nanometer scale, and it's actually in this 5 nanometer scale in Z. And here we are limited by the label that we put to these proteins, right? The size of the label limits our resolution. So we said, what if we are not limited by the label? What's the maximum that we can get with this technique? And then we switch to DNA origami structures that are a self-assembled nanostructure of DNA, and we wanted to probe the distance of one base pair of DNA. These are arranged in a 20 nanometer. It's an arbitrary distance, and these pairs are just spaced one base pair apart. And as you can see, DNA paint clearly resolves the 20 nanometer, but cannot resolve the single base pair. Instead, Resi actually resolves nicely the base pair of DNA, and for the first time, we actually achieved optical resolution of Armstrong scale, like below 1 nanometer, and in the most straightforward way of defining resolution, basically telling one object from another that are closer than 1 nanometer, that are in the Armstrong scale. And this is actually the backbone distance of the DNA, which is 7 Armstrong according to crystallography. So, and yes, the scaling law actually works very nicely. And with this, I want to thank everyone that has worked together with me in teams during my journey in the super resolution field, Fernando Stefani lab in Argentina and Ralph Jungmann lab in Germany. And thank to you very much for your attention, and I'm open to questions. Thanks so much.
Thank you, Luciano, for the enlightening presentation. Would any committee members like to pose a question? Yes, Professor Zhang Shuang.
Hello, hi, Dr. Masullo. It's very impressive talk, very interesting results. Just wonder, regarding your work on this sequential imaging. I wonder, so most of objects you are looking at is just two objects close to each other, right? So if you have many objects, very close in space, and so you have to do many different sequential sequences, right? So what's the limitation? How many sequences you can get as a maximum?
Well, that's a very, very good question. So first of all, this sequence space is really not the bottleneck, because we can computationally design hundreds of sequences, but the actual bottleneck would be how much time it would take to image. But we have optimized sequences that are relatively fast to image, and we've gone up to 30 sequences. So I would say experiment. So theoretically, there's basically no limit in the amount of sequences that we can put, but from the experimental point of view, we can get up to 30 of these sequences. We actually have published another complementary work that does 30 color DNA paint. So, but one thing that is very important to keep in mind, because this is an excellent question, is that we need to resolve whatever DNA paint cannot resolve. So DNA paint already has a resolution in the range of the sub-10 nanometer. So basically the extra thing that you need to resolve are the molecules that are within a 10 nanometer area or volume, let's say. So, and there, practically, you cannot fit many more than 2, 3, 4 molecules, actually. So Resi basically let us go into the stoichiometry definition. We can actually see the arrangement of these multimers, and then this way we can go into do structural biology. But we need to resolve 2, 3, 4, 5 molecules within this 10 nanometer limited area. Thanks so much for the question.
Thank you.
Martin?
Yes, I have a question about the limitations of this method, and I don't mean here the theoretical limitations. What are actually realistically the practical limitations you're encountering at the moment about how far you can push the resolution here?
Well, I would say the most important limitation now is the label that we used for the proteins of interest, for example, because if you use for example, primary and secondary antibody, this doesn't make any sense, because already the size of the probe that you're using is too big for this resolution to make any sense. Also, if you use nanobodies that are these fragments of a primary antibody conjugated to DNA, they are already in the 4 nanometer, 5 nanometer size. So that already limits our resolution to a few nanometers, but we cannot really go into the Armstrong scale. So to really go into the Armstrong scale, we need to directly attach a strand of DNA to the molecule of interest by some kind of click chemistry or this kind of stuff. So that's, I would say, the most important practical limitation that we have at the moment. The other things I can argue that are relatively solved and are actually not the bottleneck. That's the biggest bottleneck so far.
Okay. Thank you.
Thank you. Are there any last minute questions from the committee? Yes, Nico.
So it's very exciting that you push the limit, but I'm curious how you address the motion artifacts in your problem.
That's an excellent question. So basically, what we realized is that this method can be applied with a really good drift correction, basically that is done with post-processing, because in all these experiments we have references in our sample that are very bright. We have gold nanoparticles, hundreds of those that are imaged together with the cell of interest. They are like outside the cell, or I mean, one could think of similar things. And these fiducials are not limited in signals. So the precision which we can track the whole sample is super high. It's actually really good. And then we can correct with that. And that allows us to actually post-process and surpass the motional artifacts. We can even have fiducials in our sample, in the region of interest that we want. For example, within the origami, we can actually have fiducials to track for little motions within the origami. So this can be done by fiducial tracking and correction.
All right, thanks again, Luciano, for the very nice presentation. Let's move on to the next speaker, Danqing Wang, postdoc from Max Planck Institute for the Science of Light, Germany. Danqing, the virtual stage is yours. Please go ahead.
So hi everyone, I'm Danqing from Max Planck Institute for the Science of Light. It's a great honor to be here. And today my talk is on emerging optics from structural nanoscale cavities. So to start my talk, first I want to acknowledge my advisors for PhD and postdoc, Terry, George, Junqiao, and Wahid, and also the work presented here are not possible without collaborations from different groups around the world. So my topic is on integrated photonics. We know that for electronic circuits, the interaction of devices has approaching and falling behind the Moore's law's prediction. So what happens next? So compared to the electronic devices, photons can offer the future promise with larger bandwidth, faster modulation speed, and lower power consumption, especially among the different critical components inside. The miniaturized coherent length cells and the low loss waveguides are two key components for the future photonic circuits. Also, such integrated photonic circuits can be used in the future quantum engineering, communication, simulation, and computing applications. And in this aspect, nanoscale photonics can also offer the prospects for the room temperature operation based on this density of states and optical resonance, and also the scalable integration based on the optical cavities as a framework. And along the lines, my past research focused on two aspects. One is the generation process, and one is propagation of light. So for the generation of light, I was using the particle lattices as a system to achieve nanoscale ladders at really small scales. And also we use these particle cavities as a framework to interact with different materials and achieve enhanced single photon emission and also low threshold nanoscale ladders. And over my postdoc, I expanded my research to these new material libraries of epsilon near the materials. And we achieved this low loss and wavelength optical waveguides. So as a key outcome for the nanoscale ladders, so in the past decades, there has been efforts to try to shrink down the physical size of the laser. A major limitation behind is the diffraction limit. So how can we overcome this diffraction limit and have the smaller scale ladders that can be used for future photonic circuits, such as the lighting and the biomedical imaging? One solution is based on metals that offers surface plasmons at this interface with dielectrics. There has been many exciting research in the past from around the world, for example, Berkeley, Singapore, Tsinghua, and Peking University. And for my own efforts, I'm also using metals as a system and achieve these sub-wavelength miniaturized ladders. And compared to other systems, here we can achieve different device functionalities, for example, tonable laser emission from a single device, multiple color emission, and also low threshold nanoscale ladders. And the system we utilize is based on such a unique particles in array. And this dates back to actually 2 decades ago from Sharp's group at Northwestern, where they observed such really ultra sharp resonance when you have the particles in a structured lattice fashion. And especially when you look at what is happening in terms of this near-field interactions. So if you have a small particle that supports the local surface plasmons, the light will dissipate pretty quickly to the free space. But if you have the particles in a lattice, now the light is more confined to the particle subwavelength scales to have these hotspot regions. And what you see here is a pretty characteristic standing wave patterns from such an array structure. And in the past, in Odom group, we were able to integrate this type of nanoscale cavities with dye molecules in the solution and achieve less than the room temperature. You can see that the emission is happening vertical to the sample surface, and the laser emission peak is defined well by the underneath cavity resonance. So one of my work in the past is focusing on the structural engineering of nanoscale cavities for different functionalities. And one work is inspired by nature. So in chameleons in nature, they can change color at will, and partially because they have such a well-organized nanoscale crystals on their surface. And for us, we took this inspiration and had the particles into a flexible substrate that is made of PD mass. And in this case, upon the stretching releasing of the substrate, we are tuning the interparticle spacings mechanically by the strain. And this modulates the optical resonance of the cavity and control the laser emission mode. The result, we see this mechanical tonable lasing based on the local strains that is robust to the stretching. Especially our system shows a higher frequency of merit for the strain sensitivity compared to the system based on micron dielectric ladders. Another question we ask is how we can integrate multiple length scales to such a lattice. Here we call the super lattice, where you see is actually there's the particles spacing which is sub-wavelength, but also there's a patch spacing that is tens of micron. The surprising part for us initially is that there is a long-range coupling that is happening between these patches, which introduce such multiple resonance in the linear property. And in the case of lasing, we use dye molecules as a gain medium and achieve multiple model lasing from such super lattice structures. And what we see here is a pretty stable multimodal emission from such a super lattice design, especially compared to the conventional lasers, where if you have multiple laser emission, most of the modes will compete for limited gain, and only a specific mode will survive at a really high power. But for our system, it's pretty stable at the high powers, partially because each mode here is having a different distinct near fields. So the competition for the gain is minimized in such a multimodal laser system. Especially, we also took a further look into the underneath mechanisms for lasing by looking at the band structures. So here you can see both the modeled and the speculated and measured optical band structures from such a superlattice, where you see multiple bandage states. We found that there is a pretty good correlation between the lasing emission position and the bandage position, which means that here, based on the superlattice, we're engineering the dispersion of the different modes in the band structure, and the lasing is serving as a probe to look at the bandage state, where you can trap the light with a slow wave fashion with a nearly zero group velocity, and that's a site where we can trigger for lasing. So this also offers us future aspects like how we can engineer the lattices to further modulate the band structures and using lasing as a probe to look at what is happening inside. So beyond die molecules as a GaN medium, we also look at interactions of this cavity system with different materials. And one question we ask here is how to achieve a low threshold laser based on the continuous wave pump. So based on the result here is actually benefiting from the synergy of our low loss cavity system and such a pretty robust and efficient emitters based on upcoming particles. As you see here, these particles are the rare earth-based materials that is mostly ytterbium and erbium are serving as the key elements inside as an emitter. And for us, we integrate such a system with our cavity and achieve low threshold lasings at the room temperature. What you see here is under this continuous wave pump, we see a pretty low lasing threshold, and the lasing emission peak is defined by the cavities underneath. Especially for this system, to our knowledge, this is one of the lowest lasing threshold compared to non-scale lasers for other types of research. And this is benefiting from both such a low loss cavity and such a robust emitter from rare earth-based elements. Such a device is also pretty stable over 6 hours of operation. What you see here is almost no change in terms of the lasing emission intensity and the peak position. And beyond the upcoming particles, our system also has such a freedom to interact with different types of GaN mediums and for different elemental interaction processes. Here we can achieve enhanced nonlinear optics and modified exciton plasma dynamics, and also engineer the directional lasing emission based on the synergy with different GaN medium. And one highlight is our coupling to the quantum emitters in HBN at room temperature, which is joined with a group at Australia, IGER here. So here we achieve this enhanced single photon emission based on this intense per-cell enhancement and localize these quantum emitters in HBN to our hotspots regions. And all my postdoc work, one question I ask is how to expand the new material libraries beyond the metals dielectrics, especially to still kind of find alternative system to support such a strong near-field enhancement. And external near the materials actually serving as a pretty bizarre but also interesting material system, especially that happens in nature based on, for example, synthetic oxides materials at the plasma resonance. There are two key features from this exotic optical material. One is this pretty strongly enhanced optical fields at the interface with dielectrics. And in the past, it has contributed to enhanced nonlinear optics up to the 9th order. And another aspect is this uniform phase distributions within the yin-yin matrix, which leads to geometry invariant tuning and also broadband directional thermal emission process. And for us, we are using these yin-yin materials as a cladding layer in the conventional optical waveguide systems. What we found is that because of this extreme dielectric index contrast at this interface, so we have much stronger confinement of the light into the core regions of the waveguides, especially when the device size is going to be below to the wavelength of light. We found that our system has a much stronger confinement of the light to the core with minimized loss. And as we compare to the conventional waveguides based on the silicon uninsulator designs, we found that this system is pretty robust to the geometry invariance. For example, the bending and different curvatures to suppress the optical scattering loss. Also, it's robust to the local geometry defects. And also you can see the suppressed crosstalk in between waveguides when you have the yin-yin as a cladding layer. In this case, this can serve as a future promising system for its low loss and integrated photonic circuit. Another thing we found interesting is this multiple layers of ENZ materials. So here, because of both this strongly enhanced near fields and this uniform fast distribution of ENZ, we found that this can contribute to really long distance optical coupling, up to hundreds of micron from simulations. Also, you can see this pretty correlated near field distributions from these two layers of ENZ. We're pretty excited that this can already be probed in experiment in both linear and nonlinear optics. And this can also serve as a future kind of interconnects this long range optical coupling between different quantum emitters. So as a summary of my work, so I'm utilizing two different material systems and look at especially how to engineer the structures for different optical responses. Here we achieve mechanical tonable lasing, multimodal lasing, and also low loss subwavelence optical waveguides. Also here we care about the interaction with different types of GaN mediums for low threshold lasing and also converting lasing at room temperature and also this enhanced synchronous emission processes. For the future vision of my work, I hope to harness my background in nanoscale materials, photonics, and quantum systems, especially aim at future applications in integrated photonics and quantum photonics. For integrated photonics, I will focus on two aspects. One is generation of light and its propagation, and especially aim at this miniaturized, low loss, and multiplexed optical devices. And for quantum photonics, I found that nanoscale cavities can serve as a pretty promising system, especially for quantum photonics at the room temperature, because of this strong precell enhancement, it can elevate such a thermal defacing noise and push the operations to be closer to room temperature. And also such a system of these optical cavities can serve as a framework, for example, for the future scalable interactions between different emitters in such a cavity. So I will look for enhanced single photon emission and also this long range optical coupling between different emitters in such a system. So that's all thank you for attention, and I'm open to any questions. Thank you.
Thank you, Danqing, for the insightful presentation. Do we have any questions from the committee members? Igor.
May I have a question? Yeah, thank you, Danqing. Very, very nice work and a great outlook. I wanted to hear your opinion about the last, about your vision when you talk about integrated photonics. Most of the structures that you showed are these array types. How do you see the arrays being integrated on chip with other components?
Yeah, that's a great question. And I will just go to that slide you were asking. Yeah, so what you see here is compared to other plasmonic designs for ladders, our system is relatively unique. One aspect, I will try to zoom out here. Okay, I'll just do this one. So our system is kind of unique. The reason is we're harnessing this diffractive coupling between the particles in the lattice. So naturally, these systems will have a higher model quality and also lower minimized loss of the system. So it will help us to really achieve lasers, for example, at lower threshold or at the room temperature operation, which is beneficial for this integrated photonics. Another thing we are pretty excited about is that for these arrays, you can see that the reason they have such a strong coupling in between units is they have identical phases between each nanoparticle. And we believe that this can also work as a framework where we can put emitters at different sides of these nanoparticles and look at these long-range couplings in between, where the underneath cavity serves as the channel or the framework. And this is something that's explored yet in this community. But for the lattice arrays, there seems to be a pretty unique systems to look at this long-range coupling, especially two-photon or even multi-photon processes at the room temperature. So for the work we worked with you in the past, that is the first demo where we achieve this enhanced synchronous emission at room temperature, but there are many things we wish to explore in the future. For example, how to localize such emitters to really these hotspot regions of the plasmonic cavity, and also how you can create different emitters from on-site here and look at their interactions in the real time.
Mona.
Yeah, thank you very much for the great presentation. My question is related to previous question, specifically about those structures or that are based on rare earth compounds. How do you see the carrier lifetime reduction generally by these rare earth compounds impact lasing performance, and how do you see them being integrated with other foundry integrated photonic processes?
Yes, for these emitters we have here, which is based on the rare earth based materials. One reason we also choose this material is also they have this roughly slower decay of this ultra-fast process, which is favorable actually to this continuous wave pump. Definitely, when you have a cavity with to be close to these emitters, we have such a strong per-cell enhancement, which means that we can further reduce the ultra-fast decay lifetimes by the orders of the per-cell factors. This means that we have more like stronger emission efficiency from the device, and also have a more ultra-fast modulations in principle compared to like emitters that is bare like in air. So this not only for this kind of emitters in general, we found that the ultra-fast ultra-fast processes enabled by the cavities can, for example, in the future optical electronic devices modulations, you can have more like faster responses based on the cavity, and also have a stronger quantum yield from this kind of cavity enhancement.
Thank you, Danqing. So maybe we can have the last two quick questions from Qihua and Shuang.
Yes, Danqing, very nice talk. I have two quick questions. The first one I have is, we all know that the plasmonic system usually quench fluorescence. So I just wonder whether your dye molecules, they are directly in contact with the silver or gold nanoparticles, whether this is a significant problem. The second question I have is, as far as I understand, this emission is actually directional. It's a unique thing about this lattice, right? This also may give you some problem if you want to control the emission. How do you comment that?
Yeah, that's two pretty great questions. For the first question, which is talking about the quenching of these emitters close to metals. So for our systems, we also observe such behavior. But one nice part of the dye in a solution is that because of the Brownian motions, the dye molecules always is actually flying around in this solution. So we have such a refraction of the dye molecules that is in these hotspot regions, so that it gives us much better like stable emissions from this leather device. So partially it can mitigate this kind of quenching properties. Like, for example, we can also put some silica like protection layers if we worry about this kind of really nanometer scale quenching of the emitters. So for the second question, could you repeat that one? I'm sorry. So
the lattice give you a directional laser emission, right?
Yes, thank you for that.
How can you control that?
So what we found is that for our systems, the manufacturer is actually the guiding player underneath to control where the landing happens in terms of both spatially and spectrally. So what you see here is actually why mapping out this angle resolved emission of different landing peaks. We found that for the landing modes at non-zero K vectors here, this is where we observe such a directional emission that is not normal, but at a small specific angles to the surface. We can further engineer such band structures, for example, look at the different high symmetry points in the system, X or other different symmetry points. We found that you can achieve even stronger like modulations of the directionalities of lasing. So it's actually controllable based on how you design the lattice and control the overlap of the gain emission profile with a specific vantage point.
So final question from Sean.
Yeah, okay, thank you. Yeah, very interesting talk. Just wonder, yeah, so of course your lasing mode is a collective mode which has strong coupling among the particles. But down to the single particle level, do you have a dipole mode or some multiple plasmonic mode? So what mode is that?
Yeah, that's also a great question. I didn't go to the details because of the time limit, but in principle, we can harness different types of multipolar modes based on how we engineer the structures of this lattice. When in the very early work here, we utilize dipole modes because we utilize this in-plane interactions between particles. But later, for example, in this work, we're actually harnessing the quadrupolar high order modes. The reason is we want to preserve such a mode resonance quality over different ratios of strain. And we found the high order modes give us a pretty stable mode quality under the different stretching ratios here. And further, you can also harness different types of shape, for example, on the particles. For example, one of the work we have done is this symmetry broken nanocrystalline arrays, where we also see high order quadrupolar modes in that system. So in principle, different modes here is kind of one fundamental building block that is from unit cell level. Also, we have the freedom from the lattice, from the material systems of different metals. All this play a role to determine what type of lattice resonance cavity we can achieve and to really address that two different types of gain mediums we choose.
No, the question is, if you have this quadruple mode, why do you still have the radiation along the vertical direction? Supposedly, this quadruple mode should not have radiation along the vertical direction.
Yeah, that's also a great question. The reason is we actually call it hybrid quadrupolar mode. The reason is if you look at this charge distribution, it's not fully balanced top down. You still have a net dipole momentum that is in plane. So we still have a pseudo dipolar modes from this hybrid system. That is why you see this emission to the far field.
All right. Okay. Thank you.
Thank you.
Thank you once again, Danqing. Now let's move on to our next speaker, Jiangang Feng, postdoc from National University of Singapore. Jiangang, the virtual stage is yours. Please go ahead.
Okay. Can you see my screen?
Yes.
Okay. Thank you. And hello, everyone. I'm Jiangang Feng from National Research Fellow at the National University of Singapore. I'm delighted to introduce my research on self-assembly active nanophotonics. First, let me introduce my research focus. The market of the miniaturized photonic devices has reached $7 billion and it is expected to keep growing. Here, one key trend is to integrating more active device onto a chip for additional functionalities, such as lasers, nonlinear optics, single photon sources, and entangled photon sources. In this context, self-assembly is a cost-effective technique to incorporate multiple active quantum materials into devices with a small footprint. My approach begins with the symmetry in the physics. It can be translational, rotational, inversion, and time reversal symmetry. Firstly, symmetry is rooted in the quantum materials and enable promising intrinsic properties. Symmetry also guides the design of artificial photonic structures and control light dimensions. After fusing material symmetries with photonic symmetry, we can expect unique and multiple functionalities. For example, if we structured non-central symmetric photonic materials with rotational symmetry photonic structures, we can obtain resonant metasurface with strong nonlinear optical effect. This approach guides me to construct active photonic devices for light emission, manipulation, and harvesting. In my approach, self-assembly is important to involve diverse active materials. For example, materials like organics, perovskites, and quantum dots shows high efficiency for light emission. They also can be designed and fabricated from bottom up, which enables properties on demand and cost effectiveness. However, it is indeed challenging to involve these materials in active photonics. The first barrier is that these materials are intrinsically incompatible with the CMOS fabrication. They also show randomness in different scales. That's why we want to build a method to bridge these materials to order the photonic structures and the devices. So this is my solution. We develop a self-assembly method. We start from a confined liquid film, which contains functional materials. We apply a template to guide the deweighting process and generating capillary bridges. The capillary bridge can confine the crystal growth to build nanostructures with a high resolution down to 14 nanometers and keep long-range order of materials. Here is my first case on ultra-compact self-spin value locked laser. We make impossible possible and achieve synthetic spin value locking. Firstly, TMDC monolayers exhibit intrinsic spin value locking, but these monolayers are not very efficient for night emission. On the other hand, we have diverse active materials like game materials for low threshold lasers and single photon emitters for quantum technology. But due to the lack of the spin value locking, these materials has no valid degree of freedom and usually exhibit random emission without the control of polarization and direction. A question is that can we empower these active materials with spin value locking mechanism? Here is our design. We begin with a bound state in the continuum to enable a high quality factor. Then we open a latch onto this nanodisk and rotate this structure to extend a single unit cell to a supercell. So this strategy, we firstly obtain Brownian zone folding and a replication of photonic band in momentum space. The bottom of this band are high Q quasi-BIC mode, which serve as synthetic values. This rotating latch also imparts geometric phase, directing photons with offside circular polarizations to distinct values. After then, we monolithically integrate the perovskite materials with these optical designs by self-assembly. We achieve directional Carroll lasing with a small beam divergence, high chirality, and high emission angle. Our experiment demonstrated that the lasing emission from each valley are both high directional and pure circularly polarized. Then we also achieve the tunable spin value locking by designing the latch configuration to allow 2 full rotation within 1 supercell. We achieve a doubled emission angle compared to the previous scenario. In the third scenario, the latch undergoes 3 full rotations, yielding Carroll emission at a higher angle of 41 degrees. Because of this spin value locking behavior is independent on the material symmetry, we therefore can extend this design to all active materials. Previous work is about photonic sources, but if we want to manipulate light on chip, the weak nonlinearity of photons will be a significant challenge. In this case, I will show how to realize a ultra-fast all-optical switch. The first generation of all-optical switch relies on high-quality factor resolators to ensure sufficient interaction time, but this approach compromises response speed. Then incorporate matter excitation with ultra-cold atoms will enable nonlinearity. However, such systems show a large footprint. Macro-cavity exciton plurotons offer a compact solution for all optical switching, but typically required cryogenic temperatures. Therefore, we ask a question, can we achieve all optical switching at room temperature? We address this challenge by creating a self-assembled perovskite microwire integrated into a cavity. These microwires sustain stable exciton plurotons at room temperature. We firstly inject plurotons fluid in microwires via a source beam. Then through the introduction of localized pleuroton using a block beam, we establish an energy barrier leveraging the repulsive interaction between plurotons. By manipulate the time delay between the 2 beams, we showcase on-off control of pleuroton propagation. The real space image indicates that the pleuroton propagation stops upon synchronization of 2 beams. However, with a time delay of less than 2 picoseconds, pleuroton propagation recovers. The propagating pleuroton fluid also suggests that this all-optical switch can be cascaded with other devices to form all-optical logical gates. To transition nanophotonic innovations from the concept to impactful applications, it is crucial to large-scale integrate photonic structures into practical devices. This is what I'm going to talk. Solar cell is important to address global warming. Over the past decades, perovskite solar cell experiments are extremely rapid growth in efficiency. Now this record comes to 26.1% compared with which is comparable with silicon solar cells. The growth is mainly attributed to the advancement of materials, but this road become increased narrowing. If we want to approach the final Shockley quiescent limit, we believe that light management should be the key. For perovskite solar cells, light absorption is still inefficient in thin films, particularly near the perovskite band edge. While thinner thin film could theoretically improve absorption, they restrict the carrier transport in practice. To enable strong absorption, we integrate resonant photonic structures with solar cells. We manipulate the translational symmetry of photonic structures by designing a supercell grating with the Brownian zone folding. This method folds guided model resonance at high momentum to the Brownian zone center, which effectively enhances the photonic density of state near the band edge in the designable manner. We then fabricate photonic structures onto perovskite over a larger area. Notably, we observe a substantial increase in light absorption near the band edge. This improved absorption results in a photocurrent enhancement in solar cells. Our approach can lead to the enhancement in solar cell efficiency, and this approach also potential to improve light emission in LEDs as well. Finally, I would like to outlook the future of this field. I believe that my research over the past few years has merely opened a door. Behind this door, I can see a vast ocean of possibilities in active nanophotonics. This approach allows for the integrating accomplishments in both active photonic materials and artificial photonic structures, all guided by the principle of symmetry. I hold the belief that we will develop a wide array of nanophotonic devices along this path. Finally, I would like to acknowledge all my supervisors and collaborators. I feel that I'm so fortunate to get training in these estimate groups in the field of nanophotonics, material science, and devices, which accidentally led me to develop these cross-disciplinary researches. Thank you very much, and I would like to take any questions.
Thank you for the nice talk, Jiangang. Are there any questions from the committee members? Yes, Sean.
Yeah. Hi. Very nice talk. So a question: can you go back to the slides of this laser work with this circular disc with notches? Yeah. Okay. I just wonder. Yeah. So it seems like so to get a really high quality radiation with circular polarization, it seems like you should have a uniform coupling between the neighboring disks, right? If you go back to the previous slide.
Yes.
Yeah. However, when the notch have all the different orientations, right? So yes, will that affect the uniformity of the coupling among the unit cells?
Yes, exactly. Yeah. So I think this actually this kind of notch, this kind of active metasurface is protected by the is a kind of non-local metasurface. It means that even if the orientation of each notch has some disorders, it can be tolerant to the design. Yeah.
Okay. Yeah. So in this diagram, that's very interesting. You have a band folding, right? So you have many values. You have a +1, or whatever order. But then you can design this linear gradient of the orientation angle. So this is based on the geometric phase, I suppose.
Yes.
So then you can selectively, have the laser along certain diffraction order. So can you have some arbitrary combinations? So in all the results you have, it's always symmetrical, plus going one direction, minus going the other direction symmetrically. So can you have some arbitrary combination, among the different diffraction orders?
Yeah, actually we have in our case we have shown that if we in one unit cell, if we rotate this kind of notch with 2 rounds, we can deflect the light into higher angle. Yeah. And
that's a lasing angle, not that's a lasing angle, right?
Yeah,
lasing
it's an emission angle.
Yeah, I just wonder whether you can just selectively just let the light go along one direction, one particular direction, instead of going along both, plus 2 or minus 2 orders. So all the light just go single direction. Is that possible?
Actually, it's from the optical side, it's not possible because we do not break the time reversal symmetry. But if we using, for example, if we using combine the TMDC material with if the light, if the lasing is come from one value of the TMDC material, then it's possible to obtain a directional carrier lasing by combining the spin value log of the TMDC. Yeah.
Okay, thank you.
Okay, thank you.
Qihua.
Hey, Jiangang, I have one question about the third part. So the resonant solar cell seems to have enhancement towards the longer wavelength part, right? Yeah. It's just like this figure, for example. But we know that the material you're using is a perovskite, which has, in principle, they have a higher photon harvesting efficiency, maybe around 500 or something. I'm asking whether in your design, is it possible to try to somehow manipulate the band towards the maximum, photon harvesting spectrum range?
Yes, I think this strategy is has a very flexible, which can be extended to other solar cell system. Why we choose actually for the perovskite, even near the band edge, the absorption is inefficient. That's why we using this method to further incorporate with perovskites. So as you can see in this in the EQE spectrum, the thin film experience a faster drop of the efficiency. But if we combine the resonant structures, then we can obtain considerable high absorption near the perovskite band edge.
Okay, so this is a hybrid. This is like a methylamino alloy type of hybrid perovskite, right?
Yes, hybrid perovskite.
Okay, I see. I know on the wonder. Okay, thank you.
Thank you.
Before we progress, any quick questions? All right. Thanks again, Jiangang, for the very nice presentation. Due to our tight time schedule, we'll have to conclude the Q&A here. Thank you once again. Our next speaker is Weiliang Ma, PhD candidate from Huazhong University of Science and Technology. Weiliang, the virtual stage is yours. Please go ahead.
Okay, my voice is okay. Can you hear me?
Yes.
Okay, thank you. Share my screen. Can I start?
Yes.
Okay. Hello, everyone. It's my great pleasure to be here today to give a talk. My name is Weiliang Ma, and I'm from Huazhong University of Science and Technology. The title of my presentation today is In-plane hyperbolic polaritones in natural materials. I hope to give you a brief overview of the research we have made in the past few years in the field of controlling light propagation at the nanoscale. On the first slide, let's jump right into the main topic. I want to introduce what hyperbolic polariton is. It is a unique kind of electromagnetic mode in strongly anisotropic materials like the layered metamaterials shown here. We typically describe how light propagates in materials using an equation here. It shows the wave's momentum distribution when one of the components of the material's permittivity tensor is upside in sign to the other two. It will result in hyperbolic isopropy surfaces in the momentum distribution. There are two types, type 1 and type 2. In isotropic materials, light travels through the materials with momentum described by a circular line here. This shows that wave propagates similar in all directions and have limited momentum. But in hyperbolic materials, the momentum distribution within the materials takes the forms of an open hyperbolic curve. This means that it allows for propagation of the modes with very high momentum and very short wavelengths within the material. That is to say, we can compress light beyond the subwavelength scale. Additionally, when we get close to the asymptotic directions of the hyperbolic curves, many high momentum modes tend to travel nearly in one direction, indicating a directional propagation. And if we put a point source on the surface of hyperbolic materials, the light within the materials exhibits highly localized and directional propagation properties. And due to the strong compression of light and the ability to control their propagation at nanoscale, these two crucial properties have received a lot of attention and have some promising applications. For example, it has enabled super resolution imaging beyond the diffraction limits. And because of the open and hyperbolic IFC, it enhances the local density of states and also improves the radiation properties and also can achieve negative reflection effects among other benefits. In the early days, most hyperbolic materials were realized in metamaterials, often associated with higher losses. Additionally, the ability to compress light fields was limited by the minimum size of artificial unit cell, which hinders their applications. In recent years, there has been a lot of attention on natural hyperbolic materials due to their strong inherent entropy, whether it's hyperbolic plasmonic materials driven by anisotropic electronic properties or hyperbolic Feng materials resulting from anisotropic lattice vibration. They have all received significant interest. These natural hyperbolic materials can cover a wide range of the spectrum from ultraviolet to terahertz range, allowing for light compression at various wavelengths. Among them, one-virus materials are particularly important. Their naturally occurring layered structures make them an excellent platform for studying hyperbolic polarities. In our research, we discovered a natural in-plane hyperbolic material, molybdenum trioxide, MO3. What makes it special is that it has strong in-plane entropy, leading to the distinct optical phonos response in different in-plane directions in the mid-field region. This results in a situation where the permittivity can have different signs within the same plane. So what is the significance of this discovery? To put it simply, if we liken the typical polariton propagation to water waves, these materials allows us to give these waves a specific directions within the plane, rather than spreading uniformly in all directions. So in other words, it provides us with a new way to control the planar directions of light propagation nanoscale within a plane. Using near-field imaging techniques, we have indeed observed the entropic propagation of the polartons within MO3. Subsequently, by employing a bilayer MO3 structures with controlled their twisted angles, they achieve near one-dimensional propagation patterns within the plane, enabling canalization mode. Additionally, researchers also explore the potential of heterostructures involving the MO3 and graphene. These structures allows for controlling their dispersion and convergence characteristics of the polartons within the plane using the gate voltage, leading to in-plane negative reflection effects. Although we have already discovered the in-plane hyperbolic polartons in MO3, but there's an intrinsic limitation. The most polariton fields are confined inside the bulk volume rather than surface plasma polartons. That the field are mainly confined at the surface, which is more sensitive to the surrounding environment. So as their surface polartons can exhibit interesting hyperbolic dispersion? Answer is yes. Some people discover the mode can be at the set walls of HBN. It may have larger confinement and be more sensitive to the surrounding environment. However, no experiments have been able to directly image the intrinsic propagation of the surface hyperbolic polaritongs. So actually, we can try to understand the volume and the surface type of hyperbolic polaritongs on the plane with different optical axis orientation. If the OA is perpendicular to the plane, it may support volume modes, and if the OA is in plane, it may support surface modes. All right, we can find that the volume modes and surface modes are both specific cases. So what polaritongs looks like when OA have any other angles to plane is more like volume modes or surface modes or together with both two. But it's hard to investigate these cases in 2D materials because normally 2D materials are exfoliate from the bulk's lattice orientation that the OA is determined in the thin film. So to study these cases, it's more proper to use the bulk crystal. In principle, we can cut any plane we want and then polish them. Finally, we can have any OZ orientation surfaces. We start our research on traditional materials, calcite. Calcite is a well-known uniaxial crystals with optical anisotropy, has already been investigated for more than 300 years. The permittivity along OA is positive and perpendicular to OA is negative at the mid-infrared region. Based on its three-dimensional properties, we can perform cutting and polishing on it in any directions so that we can get calcite samples with different OA angles. Most importantly, through these tuning methods, we can easily achieve in-plane permittivity sign difference in the mid-infrared region so that we can synthesize the conditions for supporting hyperbolic polaritongs propagation. Firstly, we built our theory. We considering a case of the angle between OA and the calcite surface is 23 degrees. When we use a dipole to launch a polariton here, we can find a very similar in-plane anisotropy propagation. When we do the Fourier transform of the field distribution, we can get a polariton momentum distribution in K-space. It indicates a hyperbolic dispersion. But what is the difference of the calcite polariton compared with volume modes and the surface modes? We compiled all three cases here. For surface modes, the field is confined at the surface and is potentially decaying I and the bulk of calcite. It's mean because that the wave vector along the direction perpendicular to the interface. Thus, Kz is a purely imaginary value. But for the volume modes, it will propagate inside the bulk with a real value wave vector Kz. Now we switch to the polariton in calcite. We can find this hyperbolic polariton is more like a surface wave confined at its interface, but it holds the oblique wavefronts inside the bulk. According to the solution, we find this is mainly because of the complex Kz. We call it a ghost polariton, which we take the name ghost from a theory work. We also think the ghost mode here are from the hybridized mode of volume modes and surface modes. To say it in real space by Snow, we fabricate a mental antenna to launch the ghost polaritongs along calcite surface. We find some impressive features of this polariton. It shows confined and directional ray-like propagation at the right part of the picture. The line-wise of the polariton rays is only 2 micrometers, which is much smaller than the incident wavelengths. And the propagate distance is up to 20 micrometers, is maybe a record distance for all in-plane hyperbolic polaritongs at room temperature. It shows the low-loss nature of polariton in calcite. Recently, we developed an experimental method that combines the time domain interference tags with norm and achieve high spatial and temporal resolution using the femtosecond infrared pulse. We have observed the spatial temporal properties of the ghost polariton's propagation. The nanoscale movie on the right illustrates the entire process from the generation of the ghost polariton's and their propagation and their decay. Finally, based on these planar, confined, and directional modes of the polariton propagation, I have some simple ideas. For example, if we have a linear optical antenna that can excite in-plane hyperbolic polariton's propagation, as the direction of the polariton and the incident frequency are strongly correlated. When polaritons are excited from the two apex of the antenna, optical hotspots are formed at different positions for different frequency. If we can extract the near-field information corresponding to different positions, we can then deduce the frequency information and reconstruct the spectrum. Additionally, this can also be used to identify the different molecules at different positions. So that's all for my talk, and many thanks to our collaborators, and thanks for your attention and questions. Thank you.
Thank you, Weiliang, for the enlightening presentation. Would any community members like to pose a question? Igor.
Thank you for the nice presentation. I wanted to ask more broadly for these phonon polaritons, what's the main kind of key applications for this technology, and where can you use them?
Actually, for the phonoparitons, it's normally in the mid-infrared range at the long wavelength range. Normally, because of the differential limits, we want to make our device more smaller. We need to, so in the long wavelengths, it's more hard to do that. So for the phonopariton, we can do these things is to integrate more devices on the same scale. It's the first thing. And another important thing, I think, because in the mid-infrared range, it's the fingerprint spectrum for the molecular, and we can use the phonoparitons to focus the infinite light to a very small spot and to enhance that matter interaction and to induce the very sensitive molecular detection in the mid-infrared at their finger spectrum. I think it's some meaningful applications for the phonoparitons. Thank you.
Mona.
Yeah, thank you very much for the nice talk. Can you give a big picture comparison between hyperbolic polaritons excited in 2D materials versus those that are enabled by metamaterials with hyperbolic dispersion properties in terms of the applications they enable?
Yes. Actually, for the hyperbolic materials, we need to fabricate the matter and atom to design their effective permittivities along different directions to meet along one direction is positive and another direction is negative. So it's very flexible to design at different frequency, but I think it's some limitation because most hyperbolic materials are made by the made by the materials based on the mantle. Actually, mantle is very lossy, so the performance is not very good. And another problem is for the metal materials, the bandwidth is limited. Maybe most in the visible and infrared range, but for the 2D materials, because of their intrinsic inherent anisotropic, we can find some different materials has different band, and because of their high quality of the crystal, that will not suffer from very high optical loss. But I think for the 2D materials, the bandwidth is limited because, such as for the phonopariton materials, it will limited in their phonoresonance spectrum between the TO frequency and L frequency. So I think the bandwidth is limited for the 2D materials, but optical losses is small for this natural materials. I don't know what is not clear or for these two materials.
Thank you.
Thank you, Weiliang. I may have a question. So how do external factors like temperature or mechanical strain affect the properties and behavior of these in-plane hyperbolic polaritons?
Yes, thanks for the good questions. Actually, for the temperature, because the temperature can influence the phonoscattering for the phonoparitons. If we can decrease the temperature, it will enhance their, it will decrease their loss and make it propagation longer. And some other factors, we can use some other geometry to fabricate some geometry, or the surrounding dielectric environment also can tune its properties. And also, yes, I think. Sorry, can you repeat your questions in the last part? I don't hear it clearly.
Oh, just I asked external factors about temperature and mechanical strain. So how
mechanical
do
strain.
mechanical strain.
Yeah. Actually, for the mechanical strain, I think it's a good directions we can do. The strain will shift their phono frequency so that it will tune their dispersion, and if the dispersion are changed, so their propagation will also be modulated. So there are some works has already been investigated this based on these factors, but for the implant hyperbolic protons, maybe we can have try in the future.
Thank you, Weiliang. Are there any last-minute questions from the committee? So maybe one final question. So what future research directions do you envision in the domain of implant hyperbolic polaritons?
Okay. Actually, in the outlook, I just show some basic very simple ideas for the on-chip information. To actually, if we can tune the light propagation at nanoscale and their direction of the propagation, and they are very confined, we can use the on-chip information transfer. Because of the time limits in our work, we show a basic idea like how can we use this hyperbolic implant hyperbolic protons. We can transfer the wise of two objects, the information, the wise between two objects to transfer this information to long distance, maybe longer than 15 micrometers. So it's just a basic demo application for the we can use these things to do some on-chip information transfer. Yes.
All right, thanks
Thank
again, Weiliang, for the very nice presentation. Let's move on to the next speaker, Haoran, Associate Investigator from Monash University, Australia. Haoran, the virtual stage is yours. Please go ahead.
Thanks very much, Yating. Just let me to pull my slides up. So I guess you can see my slides.
Not yet. Yes,
not
we
yet.
can see now. Yeah.
Okay, cool. Thank you so much. Yes. Good morning, good evening, good afternoon, everyone on the audience. And first of all, I would like to give a special thanks to my nominator and the selection committee for giving me this opportunity to share our nanophotonics research on such a great, iCANX platform. So my name is Haoran Ren. I'm working as a DECRA fellow at Monash University, Melbourne, Australia. So the title of my talk today is Nanophotonics with a Twist. So basically it's two keywords. But I would like to pull this first slides out for the acknowledgement, because without these people, my colleagues and collaborators over the world, it wouldn't be possible to have all the results that I'm going to share with you today. So that's started with some motivation of my research since the start of the PhD. So basically, if you still remember, the title of the slides is having the twisted light as the keyword. So the structured light is a more broad definition of the twisted light. Why do we have to have this structured light? Because this is the potential gift the light offers us as compared to other energy carriers like electrons. You always have the binary states, but for the light you can encode the information on the multidimensional nature. So for instance, the polarization, the wavelengths, even the angular momentum, all this degree freedoms can carry the independent information. So that gives the motivation of my research in nanophotonics on two folds. First, basically just to study the structured light-matter interactions for in nanophotonics and trying to look at the fundamental aspect. And secondly, would like to trying to develop some nanophotonics devices, just trying to have a better manipulation of this structured light and hopefully create impact. So in terms of the twisted light, basically, as I mentioned, it's a small subject, small subset of this structured light. In particular, the orbital angular momentum modes carried by the helical phase. All these modes, they are theoretically unbounded, which means they have many modes, and each of them are intrinsically orthogonal to the other, which means you have the little model crosstalk when you use them to encode the information. So basically, that gives rise to many applications of using structured light. So I think the advantage of presenting the talks, a little bit in the later order, is the fact that many different concepts have been already introduced by brilliant speakers before. So let's just quickly catch up the ideas of the matter surfaces. I would like to highlight the paper published more than a decade ago by the Harvard group. Even though there's many arguments, maybe there's many earlier work for the matter surfaces already been published, but since this paper, I think the field gets really boosted. So the matter surfaces, as compared to the 3D matter materials, you don't have to really propagate the mode or the field inside these 3D structures that potentially have the additional loss. So the interfacial structures you can encode and offer already very much strong the momentum so that they can modify the Fresnel equations, for instance, for the reflection and the refraction, so that even with a certain momentum, you can also couple the light into the surface wave that are bounded on the surface. And in terms of the singularities and the structured light manipulation, or the the combination with the matter surface concept, you could think of many different examples. But overall, a couple of singularities maybe just can be classified. First of all, the singularities can be carried on the polarization degree of freedom. This is very much like, I think, Jiangang's presentation, where they show the BIC in the K-space always have the singularities, but also you can imagine the phase vortex, which is the phase singularities. This could be, could be implemented on the free space light for the wavefront shape by the wavefront shaping matter surfaces by using many different nanostructures, including plasmonics, dielectrics with different physics. You can design this wavefront shaping matter surface for that purpose. And also we've been witnessed the other type, which is plasmonics vortices or the polaritonic vortices, including the phonon examples as the last speaker showed. So that this structured light can also be generated or detected in the nanophotonic structures. So this gives rise some summary or the overview of my previous research since the PhD. As I mentioned, my research interest to focus on the light-matter interactions with the structured light, right? And we look at both near field and the far field electromagnetic wave manipulation. So in the near field in particular, so we can develop the nanophotonic chips so that they can harness this structured light detection capability, or we can make this high quality factor resonances, still now people call it a non-local matter surface, basically build up this strong resonance, and still very much rely on this near field enhancement of the field for some molecular sensing, for instance. And also very recently, we also moved some focus to the polaritonic vortices in surface phonopolaritones, which I will give one of the examples as one of the focal eye for today's presentation. And in terms of the far field matter surfaces, basically, so my previous research has been focusing on using the structured light to further increase the optical bandwidth or the capacity of this optical systems, for instance, holography and holograms, where we use different twisted light modes to reconstruct many different image results. And also recently the work in collaboration with Igor and his group. So basically we use the meta surface to be able to manipulate this single photon emitters. And also the vectorial meta surfaces can also be developed, that carries the topological features. And the last example in my talk today, I would like to give highlight is the metal fibers that we recently for this glitch, I just suddenly pressed the button. Yep. So the last example that I would like to give is the metal surfaces. Putting the metal surface on the optical fibers, where we can basically deliver arbitrary structure light modes through the fiber. So let's get started from the first example. This is in collaboration with my colleague Andrea Maccini, who is now working in the University of Milan. What we did is actually it's called multiplications of the OEM of phonopolyurethanes through this sublinear dispersion property of this surface phonopolyurethanes in the mid-infrared wavelength range. If you think of the doubling or tripling this key vector or the momenter, so basically you have to double the frequency or tripling the frequency in free space. While doing so, not many materials can equally support this light-matter interactions that much, and also you need a very large range of this frequency to do that. Well, if you have a sublinear dispersion property, similar to the plasmonic structures in the visible frequency and near IR, even though that carries a lot of loss of the system, so that not have been very much used for this purpose. But for the phonopolyurethanes in the mid-infrared, which we use the silicon carbide membrane in the large scale and the high quality, the thin film, so that this small tune of this frequency, basically you can achieve the very large variation of this linear momentum, which is a key for the phonopolyurethane wavelengths. So we demonstrate that the 3% frequency change, basically you can already doubling the linear momentum of this surface phonopolyurethanes. And we built up the theoretical framework where to study the distributions of this structure light modes in the near field. So basically it's like a dipoles that you put together into the spirals, and then let the mode to propagate and interfere in the center, where you can observe this kind of spiral structures depending on the geometry topology of the structures that you're given. For this, we also consider the loss rather than using the simple Bézier functions to decompose these OEM modes. In the near field, we also considered the thin film silicon carbide, which carries the loss as well, so that by considering loss, the mode distribution is very much like an interference pattern, rather than the case that without considering loss, that you get very much like a typical OEM pattern. So with this consideration and based on the experimental probe, the results, as you can see, that very much agreed with this theoretical framework, which means we can potentially basically just to do the mode analysis in the near field for this surface phonopolyurethanes. And what we observe here is very interesting. By fixing the same single device, same structure, right? Once it's fabricated, everything is fixed. Well, you just a very small change of the frequency that you can see the OEM contact is migrating from, for example, for this case, when you change the frequency, that OEM contact is changed from the 2 to 4. It's just by slightly change the frequency. As I mentioned, this is given by the strong dispersion of this material. And that's give us this opportunity to demonstrate the possibility to do this OEM, this multiplication in the near field for the polyretonic vortices, where you fix the structure with different geometric topological charge. And then if you look at the mode at the different frequency, for instance, with a small shift of frequency, as I mentioned, you will find that the total angular momentum that carries, of course, the spin and orbital components, but it's very much like this behavior is multiplied by the number of the modes that you give as the structure. So that this we call the multiplication. The other thing that I would like to highlight that this fact has been reported, I think, last year or something like that by the other group, but they use the H-beam, which is very much like in the lossy region for the atmospheric condition. But by thinking of the next step or the applications of this kind of work, you can think of now we probe the modes in the near field, but if you put some scatters at the center, you can also guide the light from the near to the far field. And with that possibilities, the very small change of the frequency, you can actively switch this OEM modes in the far field. That could be potentially useful, which, we work with the silicon carbide.
Haoran, sorry, due to the time limit, kindly wrap up your final thoughts in the next minute. We can address a few details later.
Sorry for the late. And this is very much transparent. The second example, I just used maybe 1 minute to quickly go through with the metal fiber concept, which we were able to produce arbitrary structured light. These are based on the 3D there's writing. And then the particular example that I would like to highlight that with the 3D metal items, you can really have the degree of freedom in the 3D. The metal atom is not bounded by the 2D plane. With that possibility, we can demonstrate the complete and independent polarization and the phase control for the generation of arbitrary structured light that can be projected to the hybrid order Poincare sphere, including the most general case, this arbitrary, the especially inhomogeneous elliptical polarization carries different OEM. And with that, I would like to summarize, hopefully, even though it's a bit like, sorry about the delay, but multiplication of the OEM in the near field, which is the kind of light matter interactions with the structured light, as well as, we can deliver this arbitrary structured light mode through the fiber, even though you don't have to propagate such mode. You just deliver on demand where these modes can be useful. With that, I would like to thank you for your attention and happy to answer questions.
Thank you, Haoran. So we may only have 2 questions from the committees. Yes, Martin.
Thank you. The interesting work there about the orbital angular momentum from this phonon polaritons. A question about that. Can you just explain when this is applied to far field modulation, what wavelengths would you be able to modulate with this?
Thanks, Martin. So based on the current, the membrane, so with the thickness of 100 nanometer, so the wavelength was focusing between the 11 to 12 micron in the mid-infrared wavelength range. So even though, with a strong field confinement, the converted surface phonon polariton, the wavelengths can be a couple of hundreds nanometer, but once you go to the far field, this is still going back to the mid-infrared wavelength range. That's the target that we are looking at, which is transparent, for the atmosphere conditions.
So if you that's a very 10 or 11 microns is a very unconventional wavelength for doing most of the applications people talk about for the use for OAM, for example, communications, let's say. So yeah. What would you be doing with the wavelengths in this region?
Yeah, thanks again for the good questions. Yes, molecular sensing could be one of the things, Martin. So basically, a lot of molecules, they have the vibration modes in the mid-infrared. So obviously, optical sensing using structured light, that could be potentially useful because light matter interactions could be small, even though the mid-infrared wavelength is huge. So there's a mismatch between these two, right? So the surface phonon polaritons basically can leverage this kind of capability. The second fold, probably again going back to the optical communication field, even though myself is not in that field, but for instance, Alan Wilder, they have demonstrated this mid-infrared optical communication in free space through this urban environment, basically. So they argue that, when you work with this optical transparency window in the mid-infrared, so like, there's a mode conservation is better. Sorry, yes. So preserving this modes through this free space is better. So that's potentially also the applications.
Okay, thank you.
Shuang.
Hi, Haoran. Yeah, thank you very much for the talk. So yeah, probably spend too less time on the last few slides. Yeah, so the meta fiber or whatever you call it looks quite complicated. Could you just explain a little more in details? What the structures are and how they interact with light.
Thanks very much, Shuang, for your brilliant question. Yes, I got a little bit delayed for the time. Yeah, so the meta fiber is actually the metal surface on fiber. And the build up the metal surface, we use the polymer structures and all the way through the 3D direct laser writing process to make the device. And I will give this example. For instance, here, this is the commercially available single mode fiber. Usually we use in the near infrared, which is the SMF28 fiber. And then we use the laser to print this tower structure to allow the beam from the single mode to be expanded into a little bit large area, which we have here the metal surface 100 micron in diameter. And then we put this metal surface, which, as I mentioned, because the pillar structures, you can control precisely the phase and the polarization down to the single pixel level, and putting them together as the metal surface, and then we can manipulate the wavefront of the fiber output into this arbitrary structure-like modes. That's what we did for this particular work.
All right. So my understanding is that those holes you punch into the fiber, right? They just try to reduce the effective index so the mode can expand. Is that right?
That's a brilliant idea, but we didn't explore that yet. So this is a tower structure that are printed in polymer. So the fiber starting from the end, we didn't polish or we didn't implement any change to the existing fiber, but we just put this the tower, the holes that on the tower, it just let the liquid to flow in to dissolve these polymers, during the polymerization, during the development process.
So then I suppose there will be some optical loss when the light, probably from the fiber into the polymer, because you have these holes, they can scatter light. And when they reach the metal surface on top, do you have an estimation, how much percentage of light is still left?
Yes, thanks a lot. But if I can draw here quickly, because single mode fiber has the core with the diameter around 2 to 5 micron, very small. Small enough that you cannot use the metal surface to efficiently manipulate the wavefront, right? So what we did is actually just let the beam to freely expand. So they will not meet any structures. This is a hollow tower structure. Inside it's a hollow, which means it's free space. So the beam is propagate out and then to meet the metal surface for the wavefront shaping.
Okay, I see. It's a cone shape. It's like a hollow. It's air.
Yeah, exactly.
Then why is it confined at this interface? Because you have a higher dielectric material surrounding it, and suppose the light should leak into the higher dielectric material instead of being blocked by the surface, right?
Yes. So this Shuang, I probably didn't get you that much. Yes, so this is free space, and then it's just covering the area that we put the metal surface in. Okay. There's no total internal reflection or whatever the other, yeah.
Okay, thank you.
Yeah, but thank you very much for your valuable questions.
Thank you, Haoran, for the nice talk and a very interesting Q&A session. I'm aware that there might be more questions, but sorry, because of the time limit, we have to conclude here. But please feel free to reach out to Haoran directly if you have any more questions. Now, let's move on to our next speaker, Shiqi Xia, postdoc from Nankai University. Shiqi, the virtual stage is yours. Please go ahead. Yes, Shiqi, you are muted. Hi, Shiqi, I think you are muted. Shiqi. Hi, Shiqi, you're muted. Oh, okay, we can hear you now. We can hear you
sorry,
now.
I just share screen, but I forgot to unmute it. Sorry about that. Okay, so now, okay. Hello everyone, I'm Shiqi Xia from Nankai University, and I'm so glad that the company can give me this chance to present my work here. And the title of my report is the Unveiling the Novel Topological Phenomena via the Photonic Platforms. And here is a brief outline of my presentation, and beginning with just part one, a brief introduction of a personal academic background. And I received my PhD in 2021 and have been working as a postdoc in Professor Jiangang's research group at Nankai University since then. And during my PhD and postdoctoral research, I focused on the field of the topological photonics and the non-Hermitian optics. And in our works, we proposed several phenomena, such as the new generic types of edge in photonic graphene, the universal mapping of topological singularity, and the first demonstration of the nonlinear reduced model guidance, and the very first realization of the nonlinear non-Hermitian topological platforms. And all these works also lead to 3 pending patents that I shown here. And be more specifically that we take the photonic lattices as a platform and focusing on the topological control of the light and their fundamental research. My major accomplishment of this area include the new topological S mode in the graphene, the unconventional flyback states, topological tuning of terahertz wave, and mapping of singularities. And combining with the nonlinear and the non-Hermitian optics that we demonstrate the nonlinear reduced non-trivial mode coupling and the topological soliding and the nonlinear tuning of the non-Hermitian topological states. And in this presentation, I'll just briefly introduce the 2 key projects of my research. The first one is the novel topological phenomena induced by the Dirac points or Dirac cone. That we know that the Dirac cone has some interesting topological properties which contribute to the existence of the edge mode and the singularity mapping. Honeycomb lattice, which have been proposed as an edge platform to demonstrate some topological properties of the Dirac points. And recently, some edge-related phenomena has been demonstrated in its photonic platforms, such as the photonic Landau levels, the orbital edge states, and the valley Hall edge states. So we can see that the edge states in the graphene has attracted a lot of attention. But in the common belief that people always think that there are only 3 types of the edge states in graphene. But in our study, we using the unit cell cutting kind of system, kind of method that we reveal there have the 4th fundamental edge state in the photonic graphene, and it can form this such one-dimensional flat band in the brain room, and it's totally different with all 3 traditional edges, and it's also different with some compacted lattice states in the 2-dimensional flat band system as we demonstrated before. So such edge states we refer it as the twig edge. And the twig edge states with it has some flat band features, but also have the topological protection from the non-trivial winding caused by the Dirac cones. And to observe such things in experiment, we developed this continuous wave laser writing method, and we can see that the position of the writing beams can be controlled by the spatial light modulator. Then, due to the nonlinear effect of the nonlinear crystal, the writing beam can create the waveguide inside the crystal. So using this kind of method, then we can demonstrate the first time the compact edge states along the twig edge in the photonic graphene, and such work has been selected as a feature in physics in PIL. The next and our other works that related to the Dirac cones is the universal topological singularity mapping from the momentum space to real space. And my main contribution on this kind of direction is the
is a universal mapping study on the lab and T-graphene lattices, which result in the pseudo-spin orbital angular momentum conversion and the vertex generation. And by exciting the Dirac cones through the pseudo-spin states, we provide the first evidence of the topology robustness during this mapping system, during this mapping process. And we also achieved the selective excitation and destruction of the pseudo-spin states in such complex structures. And the different pseudo-spin states at the output, it will carry different topological charge like vertices. So it can be a way, a new method to generate vertices in the experiment. So, and moreover, by using the periodic photonic graphene along propagation, so we are now working on a new project that is based on the universal mapping, and to realize this ladder-like generation of any order of vertices and the ring excitation around Dirac cone. So, and such vertex ladder is robust due to the protection of the non-trivial windings around the Dirac cones. So now that we move to the second key project about the topological state evolution and the nonlinear control. And first we use the one-dimensional topological structure as an example. So the SSH model has been widely used in this field to demonstrate the topological edges, to show topological lasers and the quantum communications. And we apply this topological structure to the terahertz control and introduce some nonlinear modulation of the topological states to fill a gap in the field of the nonlinear topological photonics. And to realize the nonlinear topological system experiments that we developed this set writing technique. Like before, writing beams are controlled by the spatial light modulator and put on the long side of crystal to get this one-dimensional lattices with a longer, so it can have a longer propagation distance with desired structure. So after we get these lattices, we use the tilted bar beam to pump the edge from the bulk. So under linear excitation, we can find that the output in experiment and the stellar view in simulation also that there's no light can couple into the edge waveguide due to the topological protection. But if we move to the nonlinear case, then prime beam in the non-trivial system, it will couple into the edge with some topological features. So it shows the nonlinear reduced topological mode guidance. Then we move. Then next, we show the non-harmonic system, because before we also is the harmonic system. It's a closed system and the energy is preserved. Now we move to non-harmonic system. It's an open system and it has some unusual phenomena such as the excitement point and the skin effect. And when it in place with topology and nonlinearity, it will show you some so like topological lasers and the PT solitons. But here is still one area that's hardly explored in experiment, which leads to the interplays between the topology, non-harmonicity, and nonlinearity. And what we show next is the first experiment demonstration of the center area to study the relations between the local nonlinear effect and the global PT symmetry and the roles of nonlinearity as well as the robustness versus sensitivity in such system. To do that, we apply this PT symmetric SSS model experiment. The red and blue dot denote the gain or loss of the waveguide. And using the cell writing method, we can design various of section waveguide. And we can finally get the desired non-harmonic SSS lattice in experiment. And the loss of waveguide can be modulated by changing the gaps between the sections, as shown here. And it's denoted by this transmission ratio. Okay, so now we want to have a little time to demonstrate to show what difference between the PT symmetric and not PT symmetric system. So if we have a local tuning of the center waveguide, but if we only change the real part of it, then it will not change. Then you will not break the PT symmetry. So the acting mode of the center of the defect, it will be always be symmetric. But if we can change the imaginary part of imaginary part, then the P symmetry got broken. So the eigenmodel of the effect model become asymmetrical. So these things can be seen as a signature to indicate whether P symmetry is preserved or not in the current system. So now, if we have this kind of structuring experiment, first because we all know that nonlinearity, whether it can tune the loss of system. So here we show that if this system, we get a P symmetric system at the first place, then we can find this symmetric distribution as output, which means that the nonlinearity can be used to tune the loss of the system. But also, since the nonlinearity in our system is reversible, so if we have this non-PD gain system at first place, then self-defocusing can push the system back to the PD symmetric regime and to acquire this symmetric output. And for the initial non-PD gain loss system, and so here the self-focusing will restore the symmetry. So therefore, the nonlinearity in our system can realize the destruction and restoration of the PD symmetry and the non-Hermitian tabular states. The final part is just a brief summary and the citation and impact of our works. Our works have been cited extensively cited in recent years, and meanwhile present our research at many international conferences such as CLIO, FL, and the Global Young Scientist Summit held in Singapore twice. And our works has been utilized in various of systems, and it has boosted the development of topological photonics and the interdisciplinary applications. And as in the topology of the cones, Professor Kivisa, Professor Chu, and Professor Lai describe our works as a new method for the vertex generation and light control. And for nonlinear topology, Professor Maradotti stated that our works open the door for investigating the overlaps of these planes, and Professor Chu has described our works as one of the earliest experimental realization of the nonlinear topological solitons. So our findings stimulated a great deal of research interest in the topological phenomena on the interdisciplinary area and cited by all these works. So in a brief summary, that we found a new edge states in graphene and proposed a concept of optical vertex ladder, and we demonstrated the nonlinear reduced topological mode guidance and the first realization of the nonlinear Hermitian tabular platforms. And our work was selected as the China's top 10 optical breakthrough in 2021 and optics in 2022 by Optica, and also supported by other awards and programs. Okay, so at the end, I want to express my thanks to the committees, especially to our groups and all the professors from the university. And thank you all for your time, and I'm open for the questions.
Thank you for the nice talk, Shiqi. Do we have any questions from the committee members? Yes, Martin.
Thank you for the large number of interesting and impressive results there. I have a question about, you mentioned about how you make these waveguides, and your writing system incorporated a spatial light modulator. Can you explain the process by which you're writing them and what purpose the spatial light modulator has in this process, please?
Oh, you mean the roles of the spatial light modulator in our experiment?
Yes.
Yeah, the roles is that because the size of the structure is in the macron scale, so we need to process it to control the position of the waveguide, like this. So, as shown in this animation, you can see that we use the spatial light modulator to generate some phase of the lens. Then we change because the pixel of the spatial light modulator is about 8 micron. So you can process it to change the position of the Gaussian beam it generated. So the rules of the SLM, the spatial light modulator in our experiment is like it's a controller of the position of the writing beams, and as well as the contraction of the power beams. Yeah.
So you, just to understand, where you say on this diagram from laser, is that the writing laser? You're talking about the laser using to write the waveguides?
Yeah.
Okay. And then you're using the spatial light modulator to structure the light and define where the spots are in order to write the waveguides.
Yeah. To control the position of the writing beams and also the shape of the writing beams.
Okay, thank you.
Nick.
So just wanted to kind of seek your input or comment for the PT symmetry case. Imagine that we only have 3 slits, and the middle slit is what you describe as I'll say the carrier or the pump, depending on how you call it. And you only need as much as 3 slits to bring parity left and right, and time symmetry, loss and gain into the system, right?
Yeah.
So
Yeah,
what is the added value by bringing more sophisticated problems or waveguides?
Actually, yeah, if we only want to introduce like PT symmetry, like what you said, if we only consider the time reverse symmetry and PT symmetry, the parity symmetry, yeah, 3 slides or 3 waveguides for us is enough. But here we want to see, because if we only have 3, then the topological of the system cannot be realized, because for the topological photonics, that the topological features actually come from the properties of the bulk. So if we only have 3 waveguides or 3 slices in experiment, it's hard to see the bulk. So if you don't have the bulk, then you cannot discuss what is the topology of the system. And why we consider like we said a more complex structure, because for the topology system, it will compare to the simple system in some way it may be more robust. So that's why we want to introduce more waveguides or slices in our experiment.
Thank you, Shiqi. I may also have a question. So how scalable is your photonic platform when it comes to starting larger, more complex topological systems or lattice?
You mean
the scalability of your photonic platform?
The scalability? Actually, not just in our system, because the theory for us is a common sense, and all this like wave evolution in our system actually is common and governed by the Schrödinger equation. So a lot of systems actually have some common features, like the metal surface and laser writing waveguide, and also like even in the phononic or the acoustic system. So I think that that's why we call this the fundamental research, because all these phenomena can be easily transplanted from one platform to one experiment platform to another one. So I think this is scalable you're talking about.
Thank you, Shiqi. Any last minute question from the committee? Okay, so one more question. So there is one part I didn't understand very clearly. So how did you ensure that the observed phenomenon in your platform are genuinely topological in nature and not artifacts or other non-topological effects?
Yeah. First of all, like here, because in experiment, usually we first we calculate the set structure, and so we know what is the topological mode looks like in the simulations, and also so in experiment we can observe the intensity distribution of such of the output, and as well as the phase distribution of mode. Because for us it's a discrete system, so all the mode is eigen mode. So so we can extract its intensity distribution and the phase distribution. So when we map it with the eigen mode, so we will know whether it's a topological mode or defect mode or bulk mode.
Thank you for the clarification, Shiqi. And thanks again for the very nice presentation. And with that, we have heard all our speakers today. A big thank you to everyone who presented and to our committee members for the valuable feedback. Before we conclude, I'd like to take this opportunity to invite all our esteemed committee members to share their comments, feedback, and suggestions with the rising stars on the stage, and also thousands of rising stars of the audience. So please, how about let's start with Martin.
Okay, thank you. Yes, and thank you to all of the speakers and all of the committee members for. It's been a very interesting session. We've seen a really broad range of talks here, ranging from metamaterial optics to far field imaging, but beyond the diffraction limit, and a huge range of very exciting work, which has shown not only great advances in the fundamental science, but also great potential in the applications where these methods could be used in a wide range of not only photonics, but also going out into other applications, ranging from things like communications to manufacturing and to biological applications. So I think it's really amazing example of the wide potential of the work in our field. And not only that, also a wonderful example of the extremely high quality of work which is going on in this field, including in people at the earliest career stages. And so it's been very impressive. And as a committee member, I can say it's going to be very difficult to actually go through our next step, which is to choose who the winners of the competition should be. So thank you all very much.
Thank you, Martin. And sorry, I just want to mention that actually it's not only thousands of audience. There are actually 35,000 of audience online. Yeah, so very impressive. Yeah, so Qihua, would you like to continue?
Well, yeah, I can share some thoughts. All the finalists have given such wonderful talk, within a short, limited amount of time. It is really, I think, challenging to present, to cover all the aspects of your wonderful research. I realized after I watching all these 7 talks, maybe one suggestion I have is instead of trying to cover all the exciting research you have, maybe try to reduce some of the content to give focus the story, to be selective. That's some suggestions I want to have. Hopefully this is meaningful for everyone.
Thank you so much, Qihua. Any comments from Mona?
Well, I think Martin said it very well, and I share the appreciation of the great work and the fact that we will have a very difficult job to basically score a wonderful job. Very, very impressive.
Thank you so much, Mona. Hi, Nick. Would you like to share some words with the audience?
Sure. Yeah, so I'd like to take the opportunity to congratulate all the presenters for your remarkable achievements and outstanding presentation today. And I'd like to also share my thoughts on optics is really a classical field, yet full of surprises. And I learned a lot from you guys, and I wish you take new inspirations and look for new challenges and new problems in your future career. And I think there are many miles ahead of you to bring the excitement of optics and photonics forward. Thank you.
Thank you, Nick. Sean, would you like to share your comments?
Yes, thank you. Yeah, first I would like to take this opportunity to thank Light, Light applications, for spending all the effort to organize this event, and this is really good, to have such a big audience, and I think the field of optics really have a really bright future. So I also like to thank all the finalists, for the wonderful talks. And so the topics are very diverse. I myself have learned a lot from all these talks, and I think you all have a very bright future. And I wish you all, find wish you all the best for your future career. Okay, thank you.
Thank you so much, Sean. Hi, Iga, would you like to share with us the conclusion remark?
Yeah, so I think, it's always easy to speak last, everything been said, but just extend my, well, first of all, congratulations to the finalists. It's tremendous achievement, so you should all be very, very proud. It's great to see the breadth of topics. It's very interesting over the few years to follow how the most emerging opportunities emerge and new directions come about and how new people tackle these new problems. So it's really great to see how people don't afraid to engage with new research directions, and you should all be proud of that. And it's also interesting to see how people move from place to place and follow the mobility. So do use this opportunity to network among yourselves and of course amongst the committee members and of course you youngsters, the panelists and the participants. And thank you also to Light and to the organization. It goes, I think, few years and flawless. So I hope to also I hope that you will continue with this tradition of the Stars of Light. So thank you again.
Thank you, Iga, and thanks so much for all our distinct committee members. Your expertise and reflections and the encouraging words are valuable. I'm certain everyone attending will benefit from hearing your perspectives. So once again, thank you to everyone for your active participation and engagement for the Rising Stars of Light event. We look forward to seeing you all during next week's faculty track. Have a great day and wish you all the best in your research endeavors.
Hey guys, I'm Light, Science and Applications, a 10-year-old journal. I suppose all my readers are much older than me, so you can also call me Baby Light, LSA. Back in 2012, my sponsors and publisher gave birth to me. A young blood with nothing but courage jumped to the optics world. As an infant, I was deeply attracted to the fascinating universe of optics, so I ran and ran, never tired of running towards the distance and unknown. When I was 3 years old, I got an impact factor of 14.603 and became the top 3 twinkling star in the world. Since that day, this glorious halo has been sticking with me. Along my journey, I was reported by CCTV, NHK, Unicolor, Phys.org, and hundreds of media. The spotlight is everywhere, but I knew I could not get lost. I still had a long way to go. So I launched my annual tradition of light conferences to incubate brainstorms. I initiated Rising Stars of Light to breed those brilliant youth. I founded Light Online Talks to pave the way of communication through the COVID. I started Light People to share the insight of our pioneers. Gradually, I became bigger and stronger and reached the first mountain peak in my life. There I shouldered many heavy-weighted researches. As my journey continues, I began to travel across continents and build up my baby branches in Beijing, Shanghai, London, Paris, Los Angeles, Sydney, Singapore, In Hong Kong, I was also selected by UNESCO's International Year of Light and International Day of Light as a golden partner. Look, they always reach out their warmest arms to welcome your visit. But there is no everlasting happiness. My growth pains arrived along with the fame. I was criticized for publishing too few and too slow. Luckily, what doesn't kill me makes me stronger. After digesting and coping with criticisms, I grew even faster with the help from my editors, authors, reviewers, and readers. Today, I publish the most and fastest among top 5 optics journals. I guess this is my best 10-year-old gift. Since last year, I had 3 infant sister journals, E-Light, Light, Advanced Manufacturing, and E-Gastroenterology. With their joined hands, we are devoted to serving the optics community with better, broader, and brighter platforms. We're coming for the jewel research in the optics crown. Hey guys, I'm Light, Science and Applications, a 10-year-old journal. I suppose all my readers are much older than me, so you can also call me Baby Light, LSA. Back in 2012, my sponsors and publisher gave birth to me. A young blood with nothing but courage jumped to the optics world. As an infant, I was deeply attracted to the fascinating universe of optics, so I ran and ran, never tired of running towards the distance and unknown. When I was 3 years old, I got an impact factor of 14.603 and became the top 3 twinkling star in the world. Since that day, this glorious halo has been sticking with me. Along my journey, I was reported by CCTV, NHK, Eureka Alert, Phys.org, and hundreds of media. The spotlight is everywhere, but I knew I could not get lost. I still had a long way to go. So I launched my annual tradition of light conferences to incubate brainstorms.